So today is we will discuss about dual nature of radiation and matter. Initially, for optical phenomena, there was a theorem given by Newton, which is known as Newton's corpuscular theory, according to which light has been considered as consist of very tiny particles having very small mass. They are not massless, according to Newton. They have very small, negligible mass. And using that theorem, people are able to explain the known optical phenomena up to that period, that is reflection, refraction, dispersion of light, very efficiently. So people were not even in a position to hear anything else of Newton's corpuscular theory. So when we'll discuss optics, we'll learn at this juncture, Huygens has given one theory which is describing light as a wave, which is known as wave theory of light. But people were not ready to accept his theory unless more than 100 years later, one experimental evidence comes in form of the double slit interference experiment, that which the outcome of that experiment cannot be explained without the help of Huygens wave theory. It cannot be explained by any other theory except the wave theory. So then the other optical phenomena were invented, discovered, like diffraction, polarization, which cannot be explained on the basis of Newton's corpuscular theory. On the other hand, Huygens wave theory efficiently explaining the old optical phenomena like reflection, refraction, dispersion, as well as interference, diffraction, and polarization. So people become convinced that light is of wave nature. Then some contradictions. Yes, yes. Say.
So the way current, the way electron travels connected in bodies one by one to form current or the electricity. That so light is not like light has a mass, but light
has no mass. Light has no mass. Light is a wave.
Place or yeah. Is it objectless or is it multiple objects connecting to each body like the way of the electron?
I'm going to answer your question one by one. Okay.
Okay.
I think I have understood your question. Your question is how light is traveling from one body to another body. Is it?
Yeah. Yeah.
So Huygens, according to Huygens theorem, light propagates in the medium in form of wave. Then the problem comes, propagation of waves required some intervening medium. But then what is the medium between sun and the earth? How light is coming from sun to earth? At that time, they have considered the concept of a hypothetical medium called ether, which was not supported by the experimental evidence. Michelson-Morley interference experiment is there, which do not support the concept of ether, existence of ether. Then the electromagnetic theory given by Maxwell which explain very successfully that light is a electromagnetic wave. So it is not a wave of matter. So it is basically it is not an elastic wave. So it does not require any medium. It is the wave of field, electric and magnetic field. So it can travel in vacuum. Okay. So up to this, everything is okay. That light is a wave, is an electromagnetic wave. It is a transverse electromagnetic wave, and it travels. It can travel in vacuum. It requires no medium for traveling. Okay, and basically, as every wave carry, light also carries some energy. But the problem occurs when some other phenomena discover one by one after one. First of all, black body radiation, then Compton scattering, then photoelectric effect. All these phenomena cannot be explained on the classical wave theory, on the basis of wave theory. It required something else. So it was Planck who first says that light is quantized. Quantized means it is
Small packets of
it
like
is
that.
according to Planck, light emits or absorbs in form of energy packets.
Packet. Yeah.
Einstein further says not only light emits and absorbs, also it travels in form of energy packets. So now this new corpuscular theory, particle nature of light, which can successfully explain the phenomena like Compton scattering, black body radiation, photoelectric effect, but cannot be able to explain interference, diffraction, polarization, reflection, refraction. Then what to do? Then people has convinced that light has dual character. In certain situation, you can only observe its one character only. You cannot observe both the character in a single experiment. Till now, no such experiment has been devised in which we can get the evidence of existence of dual nature of light in a single experiment. But in experiments like phenomena like interference, diffraction, polarization, deflection, refraction, dispersion, light behaves as wave. But some other situation, in case of photoelectric effect, black body radiation, or Compton scattering, light behave as a particle. So this is the starting. Okay, that wave has dual character. It can show some wave-like character. Also, it can show some particle-like character. Okay. So first we will start with free electrons. The conductivity of metals. Actually, in our syllabus, we have to discuss only photoelectric effect. So as the background of photoelectric effect, let's have some discussion over how electronic transportation occurs in medium, in metals. In metals, we have free electrons. Now, free electron means the electrons in the outer cells of the atom are very loosely bound. They move about freely throughout the lattice. Okay. These electrons are very loosely bound. Now, when these atoms are, we have already discussed these portions in electrical conductivity of metals. Okay, when these atoms are placed in crystal lattice, these loosely bound electrons get detached from the atoms. These electrons loses their identity from which atom they are originated. They forgot that identity, and these electrons are shared by all the atoms, and these electrons are free to move throughout the lattice of positive ions. These electrons are called free electrons. The free electrons, however, remain confined in the conductor and cannot leave its surface at ordinary temperature. Okay. This free electron remains confined in the conductor and cannot leave the surface of it. Whenever the electrons will leave the surface, there will be electron deficiency in the rest of the metal. So there will be a positive charge, positively charged, will created in the metal surface, and this positive charge will pull the negatively charged electron by electrostatic attractive force and will pull it inside. Okay. So the moment that electron comes out of the metal, and electron comes out of metal, what will happen?
We'll get at okay.
The metal surface acquires a positive charge
Charge,
with
yeah.
an negative charge minus E. Then the metal surface acquire an equal positive charge plus E. So electrostatic attractive force will pull the electron in the metal. So to detach an electron, we need to supply. Okay, that means there is a potential barrier at the metal surface. Now, an electron need to overcome that potential barrier to just escape from the metal surface.
Otherwise, it will be again get attached to the.
Yes, yes. Overcome this potential barrier to just escape from the metal surface. So we need to give some energy from some external sources. We need to supply energy externally to pull out one electron. Okay. Now the minimum amount of energy which is required by an electron to just escape from the metal surface is called the work function of the metal.
So, is it different for different material?
Yeah, yeah. The
This have to be
minimum,
okay.
yeah, it should be amount of, it depends on the strength of electrostatic force. Now, different metal has different structure, and
Yeah, obviously.
so they will have different electrostatic force acts on this escaping electron. Okay.
Mm.
So the minimum amount of energy required by an electron to just escape from the metal surface without any kinetic energy is called work function of the metal. So it is the minimum amount of energy which will be spent to overcome only the potential barrier. And the electron just come out of the metal surface will be at stationary conditions. It will not move anywhere. Okay. It will have zero kinetic energy. Then that amount of energy is called the work function. Now, work function depends on the nature of the metal and the condition of the surface. Okay. Work function depends on the nature of the metal and two, condition of the surface. It is generally denoted by W naught or phi naught symbol of work function. Expressed in the unit of electron volt. Now, what is electron volt?
Electron volt. Okay.
1 electron volt, it is given in the abbreviated EV, small e,
Small
capital
e.
V.
Okay.
1
Yeah.
EV
Measurement.
is the kinetic energy gained by an electron when it is accelerated through a potential difference of 1 volt. So energy gained by electron is equals to work done by electric field, which is equals to Q into V. So 1 EV is equals to 1.602, which is the charge of electron, 19 coulomb into 1 volt.
Yes.
So it is equals to 1.602 into 10 to the power minus 19 joule. 1 EV is equals to 1.602 into 10 to the minus 19 joule. Okay. Now, different metal has different work function. I'm sending you a list of metals having different work functions. So you can see cesium has work function of 2.14 eV, potassium 2.30, sodium 2.75, calcium 3.20, molybdenum 4.17, lead 4.25 eV, aluminum 4.28, mercury 4.49, copper 4.65, silver 4.70, nickel 5.15, and platinum 5.65 eV. Now, lower the work function, higher the possibility of electron emission. Lower the work function, higher the possibility of electron emission. Okay.
Okay.
We have to provide less effort for electron emission. Now, electron emission, what do you mean by electron emission?
Emission of electron.
Yeah, the phenomenon of emission of electron from a metal
Rate.
surface is called electron emission.
Is it a rate of emission?
No, it is a phenomenon of emission.
Just simply the phenomenon.
Yeah. Phenomena of emission of electrons from a metal surface is called electron emission. Now, this electron emission can be done by different process. Okay. Actually, we need to supply energy externally we need to provide energy to the electron externally so that it can overcome the potential barrier at the surface of the metal. Now we can supply energy in different ways. We can supply thermal energy, we can supply electrical energy, we can supply energy of light, or we can use some other particles or other electrons to collide with the free electrons and to emit. Okay, so accordingly, they have classified into 4 groups. First is thermionic emission. Here, the metal is heated.
Heated thermal process.
Free electrons get sufficient thermal energy. Come out of metal. The emitted electrons are known as thermoelectrons or thermions. Okay. Then comes field emission. Or cold cathode emission. Why it is called cold cathode? Because here we are not hitting the cathode, not hitting the emitter. Okay. What is happening?
Okay.
Metal surface is subject to a very high electric field. Of the order of 10 to the power 3 to 10 to the power 8 volt per meter. Electrons are emitted. They acquire kinetic energy, they gain energy due to this electric field from the electric field and able to overcome the potential barrier and will come out of the this minute. So the electron emitted in this way are called field electrons. Then come photoelectric emission. When electromagnetic radiation of sufficient high frequency, EM radiation of sufficient high frequency incident on metal surface, electrons get energy from the EM radiation, comes out of metal surface. Electrons emitted in this process are called photoelectron. And last one is the secondary emission. A fast moving electron strike a metal surface. Transfer of energy. Transfer energy to the free electron. Emission of electron. The electron emitted in this process are called secondary electron. Because the electron which is hitting the surface is known as primary electron and the emitted electrons are known as secondary electrons. So these are the broad classification of electronic emission. Yes.
Emission is the priority naming. That is the.
Yeah, we want to take out electron from the metal surface. This is our prime motto. This is our motto. Okay, so our prime motto is emission of electron. Our prime motto is emission of electron. Now, these are the different process. Out of this four process, we are now interested with this. The photoelectric emission of electron or photoelectric emission, which is also known as, this phenomenon is known as photoelectric effect. So when light of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface. This phenomenon is called photoelectric effect. When light of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface. The phenomena is called photoelectric effect. It was discovered by Heinrich Hertz in 1887. Okay. What is the observation of Hertz? Hertz found that high voltage sparks passed across the metal electrodes of detector loop more easily when the cathode was illuminated by ultraviolet light from an arc lamp. While demonstrating the existence of electromagnetic waves, Hertz found this, that high voltage sparks passed across the metal electrodes of the detector loop. We have described that experiment, Hertz experiment, but when this metal surface is illuminated with UV light from an arc lamp, these high voltage sparks are in the detector loop passed more easily. Okay, so the ultraviolet light falling on the metal surface cause the emission of negatively charged particle when which are now known as electrons into the surrounding space and hence enhance the high voltage sparks. And there is a observation. This is Hart's observation. Then another observation by Holwatz and Leonard. During 1886 to 1902, William Holwitz and Phillips Leonard investigated the phenomena of photoelectric effect emission in details. Okay. Initially, they used a zinc plate and connected it with a gold leaf electroscope, which was initially charged with positive charge. Okay. So when UV radiation fall on it, ultraviolet light, some protoelectron will come out. Then the zinc plate will become more positive and the deflection will increase. Deflection will increase. Okay. So from this experiment, they shows that uh, existence of photoelectric effect has been confirmed using this experiment also. So both Hart's experiment and Holwich and Leonard's experiment confirms the existence of photoelectric effect. So if he had made the observation, three observation. First of all, if this electroscope is uncharged, then it will become positively charged. If the electroscope is negatively charged, then it will become uncharged. And if the electroscope is positively charged, it will become more positively charged. Okay. So there are three observations. One, uncharged if initially negatively charged. Secondly, positively charged if initially uncharged. And third, more positively charged if initially positively charged. So that confirms that when UV light falls on this zinc plate is become positively charged. This confirms that when UV light falling on this zinc plate, the zinc plate is becoming positively charged. That means some electrons is coming out of this zinc plate, so that this zinc plate is becoming positively charged. Okay.
Hmm.
So in conclusion,
Okay.
this is actually experiments of Holwich. Few years later, Leonard observed that when ultraviolet radiation are allowed to fall on an emitter, there is a cathode, there is an anode, there is a battery, and a micrometer. As the cathode and anodes are separated from each other, this is the quartz bulb. So there should not be any current, but this is evacuated glass tube or evacuated quartz tube, quartz bulb, evacuated.
Vacuum theory.
Yes, that means air pressure is very small. Okay. Now, when some UV light is allowed to fall on this emitter, allowed to fall on this emitter, a current flows into the circuit. So he explained in this way that when UV light is falling on the cathode, then electrons are emitted from the cathode, and due to the presence of this accelerating voltage potential difference, these electrons are accelerated towards the anodes, and the circuit is get completed. So we get current. Initially, actually at that time, these negatively charged particles was not discovered, and in 1897, J.J. Thomson discovered electron. 1897, J.J. Thomson discovery of electron. After that, all these negatively charged particles are identified as electrons. Okay. And Leonard argued that when ultraviolet light is incident on the emitter plate, that means on the cathode plate, it causes the emission of electrons from its surface. These electrons are attracted by the positively charged collector plate so that the circuit is completed and the current flows. This current was called photocurrent. Emitted electrons are termed as photoelectron, and the current in the circuit is photocurrent. Okay. Hurwitz and Leonard also observed that when the frequency of the incident light was less than a certain minimum value called threshold frequency, no photoelectrons are emitted. Hurwitz and Leonard also observed that when the frequency of the incident radiation was less than a certain minimum value called threshold frequency, no photoelectrons were emitted.
Threshold energy is related, then threshold frequency and
Threshold frequency.
yeah, and to
During that time, like the energy, we know during that time the only the wave theory of light was there, and according to that, energy is proportional to the amplitude, that means intensity of the light. Amplitude square or intensity of the light. Energy is proportional to the amplitude square or intensity of the light wave. And energy is not related to the frequency. According to the wave theory of light, energy is not related to frequency, is related to intensity. So the phenomenon of emission of electrons from a metal surface when electromagnetic radiation of sufficiently high frequency are incident on it is called photoelectric effect. Photo means light, generated electrons, so it is called photoelectrons. Different substances emit photoelectrons only when exposed of radiation of different frequencies. Alkali metals like lithium, sodium, potassium, cesium, rubidium are highly photosensitive. They emit electrons even when visible light with visible lights. Metal like
visible.
zinc, cadmium, magnesium, aluminum responds only for ultraviolet radiation. X-ray can eject electrons even from heavy metals. Okay. So for different metals, you need different threshold frequency. So there should be some relation of this threshold frequency with the work function of the metal. It has been found as the work function of the metal is increasing, the frequency is also increasing. So there should be some relation between frequency, threshold frequency and the work function. We will come to that point. Now there are different experimental study done by Leonard and Millikan, a series of experimental study done by Leonard and Millikan, and that reveals the different properties of photoelectric effect. So let us discuss this experimental. Just a minute. So extensive study of photoelectric was made by Leonard and Millikan. Let us first draw the experimental setup. There is a glass tube with a quartz window. It is evacuated to very low pressure. There is an emitter, cathode, C, and there is a collector, anode A. They are connected with a microammeter, and a voltmeter is connected across it, and they're connected to a potential divider. Circuit. and battery, and the key, tapping key, sorry, plug key. It is a high tension battery. This is a quad window. There is a source of light. Light is incident on this photosensitive plate. Then electrons will emit and will accelerate it towards the collector. And this is a evacuated glass tube. So this is the experimental arrangement of this is potential divider. This is the experimental arrangement of Millikan and Leonard. They have studied effect of different things like effect of intensity of light, effect of potential, then effect of frequency, and then draw different conclusions about the phenomenon. First, let us consider effect of intensity of light. Actually, they measure the photocurrent and how the photocurrent is changing with intensity of light, with potential difference, and also with frequency that they have measured. Okay. Now, if we allow radiations of a fixed frequency, so here of fixed frequency, the frequency should be greater than the threshold frequency of the metal. The accelerating potential difference between A and C remains fixed. So frequency and potential difference, accelerating potential difference remain fixed between the two electrodes. Then the photoelectric current, photocurrent, if we plot photocurrent as a function of intensity of light, we get a straight line passing through the origin. Increase of photocurrent means what? Increase of photocurrent means increase of emitted electrons per unit time. Number of photoelectrons emitted per second is proportional to the intensity. Photocurrent
is the photocurrent
is proportional to number of photo electron emitted per second.
The rate of photocurrent.
Yes, rate of photo emission. So number of photoelectron emitted per second is proportional to intensity of light. Okay, intensity of light. Secondly, effect of potential. Intensity fixed. Fixed frequency. Again, the frequency should be greater than the threshold frequency. The incident radiation and increase of positive potential on plate A gradually, it is found that the photoelectric current increases with the increase of the accelerating potential till a state is reached when the photoelectric current becomes maximum and does not increase further. If we do something like this, now after a certain value, this photocurrent becomes saturated. That means it will become maximum. It will not increase. Now at this moment, if you increase the intensity of light, photocurrent will further increase, but again it will get saturated. Or again, here I1 is less than I2 is less than I3. So this type of effect has been found. But now, if we use some negative potential, then it is found that photocurrent will decrease and will become zero at some point minus V naught. And this potential is independent of intensity. So for any light of any intensity, but of a fixed frequency, the stopping potential is fixed. Okay. So the value of the retarding potential, the of the retarding potential value of the retarding potential at which the photocurrent becomes zero is called cutoff or stopping potential for the given frequency of the incident radiation. So maximum value of the current depends on intensity, but stopping potential does not depend on intensity. Maximum value of the current depends on intensity, but the stopping potential does not depend on the intensity. Okay. Now, for a given frequency of incident radiation, photoelectrons are emitted with all velocities ranging from 0 to a maximum value Vmax. For a given frequency, photoelectrons emitted with all velocities ranging from 0 to a maximum value Vmax. Now, at the stopping potential, no two photoelectrons are able to reach the anode. At the stopping potential, no photoelectron, that is, even the photoelectron with maximum kinetic energy can reach the collector plate. So the work done by the stopping potential on the first state electron must equal to the kinetic energy. Work done by stopping potential on the first state electron must be equal to its kinetic energy. So Kmax is equals to half mv max square should equals to E into V naught. Is it okay?
Yeah.
Where Kmax is the maximum kinetic energy, m is the mass of the electron, Vmax is the maximum velocity of the electron, E is the charge of electron, and V naught is the stopping potential.
So,
So for a given frequency, stopping potential is independent of intensity.
yeah, absolutely.
And this in turn implies that maximum kinetic energy of photoelectron is independent of intensity of incident radiation. For
Okay.
a given frequency, V naught is independent of intensity. So the maximum kinetic energy of electron, emitted electron, do not depend on intensity. Okay, of incident radiation. Intensity of incident radiation has no effect on the maximum kinetic energy of the emitted photoelectron. Okay. Next effect is the effect of frequency. Now,
Effect of
intensity
frequency.
remain fixed.
Yeah.
To study the effect of frequency on photoelectric effect, the intensity of incident radiation at each frequency is adjusted in such a way that the saturation current is same each time when the plate is at positive potential. Okay. So to study the effect of frequency on photocurrent for a photoelectric effect, the intensity of incident radiation at each frequency is adjusted so that in such a way that the saturation current is same each time. Now, if we plot the photocurrent as a function of anode voltage for different frequency, now as you increase the frequency, the stopping potential will decrease, or stopping potential, value of the stopping potential will increase in negative direction. Here, nu3 is greater than nu2 is greater than nu1. So, frequency has no effect on saturation current. We can't say that. Stopping potential decreases value increases, but in negative direction. Stopping potential decreases with increase of frequency. So the maximum kinetic energy is depending on the frequency of the incident radiation. Frequency of the incident radiation decides the maximum kinetic energy of the emitted electron. Now, if we plot stopping potential as a function of frequency of incident radiation, then the graph will be like this. This is for metal A, this is for metal B, This is nu zero. This is nu zero dash. This is nu greater than nu zero. This is nu greater than nu zero dash. So this nu zero is the threshold frequency below which no emission is possible. But as you increase the value of frequency above the threshold, the stopping potential is also increasing. For different metal, you will get a parallel graph, but the values are different. For different metal, you will get parallel graph. So we can conclude the stopping potential increases linearly with frequency nu of the incident radiation for a given photosensitive material. And secondly, there exists a certain minimum cutoff frequency for which stopping potential is zero. There exists a certain minimum cutoff frequency below which the stopping potential is zero. The minimum value of the frequency of the incident radiation below which the photoelectron emission stops altogether is called threshold frequency. The minimum value of the frequency of incident radiation below which the photoelectric emission stops altogether is called threshold frequency. And thirdly, for two different metal A and B, these graphs are parallel straight lines. For two different metals A and B, these graphs are parallel straight line. That is, they have same slope. But the threshold frequency are different for different materials. Okay. The above observations imply two important facts. The above observations imply two important facts. One, the maximum kinetic energy of photoelectron increases linearly with frequency of the incident radiation. The maximum kinetic energy of the emitted photoelectron increases linearly.
Sir, your video is clear. Yeah, now it's okay.
The maximum kinetic energy of the emitted photoelectrons increases linearly with the frequency of the incident radiation.
Mhm.
But independent of intensity. And secondly, for a frequency nu, the incident radiation less than the threshold frequency. For frequency nu less than nu naught, frequency, no photoemission is possible. Howsoever large is the intensity of the incident radiation. Howsoever large is the intensity of incident radiation. So once the frequency of the incident radiation exceeds the threshold frequency, the photoelectric emission starts instantaneously. If nu is greater than nu naught, photoemission starts instantaneously. Even if the light is very dim. That means the intensity is very low. The time interval between the incident radiation and the emission of electron is of the order of 10 to the power minus 9 seconds. This is very important. The time interval between the incidence of radiation and emission of electron is of the order of 10 to the power minus 9 seconds or 1 nanosecond. So this is very important. On the basis of this experimental results, On photoelectric effect, Leonard and Millikan gives the following laws of photoelectric emission. On the basis of the experimental result, Leonard and Millikan gave the following laws. First law, for a given, there are four laws. For a given photosensitive material and frequency of incident radiation, for a given photosensitive material and frequency of incident radiation, frequency of incident radiation, obviously it should be above the threshold frequency. Below threshold frequency, there will be no emission. The photoelectric current is directly proportional the photoelectric current is directly proportional to the intensity of light. It is directly proportional to the intensity of light. The saturation current is directly proportional to the intensity of the incident radiation. Second law, for a given photosensitive material, there exists a certain, just a minute. Second law, for a given photosensitive material, there exists a certain minimum cutoff frequency below which no photo emission is possible. However high the intensity of the incident radiation. The frequency is called threshold frequency. The minimum cutoff frequency third law. Above the threshold frequency, the stopping potential or equivalently the maximum kinetic energy of the photoelectrons are directly proportional to the above threshold frequency, the stopping potential or equivalently the maximum kinetic energy of the emitted electrons is directly proportional to the frequency of incident radiation. But is independent of intensity. Okay. And fourthly, so what are the laws? First law, for given material and frequency of incident radiation they should be above the threshold frequency. The photoelectric current directly proportional to the intensity of the light. The saturation current is directly proportional to the intensity of the incident radiation. And for a given material, there exists a certain minimum cutoff frequency below which no photoelectron emission is possible, however high the intensity of the incident radiation. The maximum cutoff frequency, the minimum cutoff frequency is called the threshold frequency. Maximum cutoff wavelength, there is a wavelength is associated with frequency. So maximum cutoff wavelength above which no emission is possible is called the threshold wavelength. Above threshold frequency, the stopping potential or equivalently the kinetic energy of the emitted electron is directly proportional to the frequency of the incident radiation, and it is independent of the intensity. Okay. And fourth
Okay.
law, that is also very important, that the emission is instantaneous. The photo
Instantaneous.
emission, yes, is instantaneous. Instantaneous process. The time lag between the incident light radiation and the emission of photoelectron is very small, even less than 10 to the minus 9 seconds. Time lag between the incidence of radiation and emission of photoelectron is very small, of the order of 10 to the power minus 9 second.
Every minute, how many emission will occur? We don't know even.
Yes, what we want to know?
Every minute or an hour, the
You can
rate of emission.
rate of emission per second is given by the photo current.
Yeah.
Okay.
The time interval is very short because of the reason.
No. I'm going to that point.
Yeah.
Now, the classical wave theory has failed to explain the observed photoelectric effect. According to wave theory, light is an electromagnetic wave. Electromagnetic wave consisting of electric and magnetic field. With continuous distribution of energy over the region with continuous distribution of energy over the region which the wave extends. Now, this wave picture of light could not explain the basic features of photoelectric effect. This wave theory could not explain, could not able to explain the basic features of photoelectric effect. Now, according to the wave theory, when a wavefront or light strikes the metal surface, the free electron at the surface absorb the radiant energy continuously. Wavefront strikes the metal surface, free electrons absorbs the energy continuously. Greater the intensity of incident radiation, greater the amplitude of the electric and magnetic field, and greater the energy density of the wave. Greater the intensity, greater the amplitude, and it implies greater energy density. Hence, higher intensities should liberate photoelectrons with greater kinetic energy, according to wave theory. Should liberate electrons with higher kinetic energy, with greater kinetic energy. But is contradictory to experimental result. According to our experimental result, maximum kinetic energy is independent of intensities, depends on the frequency only. According to experimental result, the maximum kinetic energy of emitted electrons is independent of intensity. Secondly, no matter what the frequency of the incident radiation is, light wave of sufficient intensity over a sufficient time should be able to impart enough energy required to eject an electron from the metal surface. Thus, the wave theory fails to explain the existence of threshold frequency. According to wave theory, no matter what the frequency is, light wave of sufficient intensity over light wave of sufficient intensity over a sufficient time should be able impart enough energy required to eject the electron required to eject the electron from the metal surface. And thirdly, wave theory fails to explain the instantaneous nature of photoemission. The energy of light wave is smoothly and evenly distributed. According to wave theory, energy of light energy of light wave is smoothly and evenly distributed, across its advancing wavefront. Each electron intercepts an insignificantly small amount of this energy. Each electron intercepts an insignificantly amount of this energy. So it should require a finite time to escape from the metal surface. So it should require a finite time to escape from the metal surface. So the three basic characteristics of photoelectric effect cannot be explained on the basis of classical wave theory. Now, to explain these theories, we need some other, explain this observation, we need some other theory that was given by Einstein in 1905. Explain the photoelectric effect on the basis of Planck's quantum theory, according to which light radiation travels in the form of discrete photons. The energy of each photon is h nu, where h is Planck's constant and nu is the frequency of light.
Yeah.
We will discuss the details of this Einstein's photoelectric effect in next class. Okay.
This was in this also was this is the part given in the class 11 of chemistry.
Okay.
Uh, the atomic structure, Planck's constant, and Einstein gave that
That's
E equal.
different thing. Planck's constant is given in Bohr's theory, Bohr's
Yeah.
atomic theory. Okay. This H. But here we will discuss photoelectric effect on the basis of Planck's quantum theory. Okay.
Yeah, photoelectric wave was given there. Yeah.
Photoelectric wave was there.
Some sort of discussion that dual nature of the
Okay.
particle.
That may be.
A small